This is a typical heating curve. Heating curves usually begin with a solid below its melting point. Then the solid melts, changes into a liquid. Then the liquid increases its temperature until it reaches its boiling point. Then the liquid boils at constant temperature. And then we finally increase the temperature of a gas. So we have solids right here. Now a solid has the lowest kinetic energy, and the intermolecular forces of attraction are the greatest. Now in this example, we're going to be talking about water. In other words, we're going to want to calculate how much energy is needed to change water from a solid as ice below its melting point up to steam at this temperature up here. Now we can't do it in one step. We're going to have to do it in 5 individual steps. We're going to have to change water as ice and then bring it up to the melting point. We're then going to melt it. Then we're going to heat up the water. Then we're going to boil it or vaporize it. And lastly, we're going to heat up the temperature of the gas. So now, let's look at the problem we're going to want to solve. We want to change 15 grams of water as ice at negative 40 degrees Celsius, and we're going to want to change it to 15 grams of water as a gas, steam, at 130 degrees Celsius. Notice that we're still working with water. Ice and steam are the same chemical compound, water. Phase changes are physical changes. They are not chemical changes. Now we're going to have to consider what formulas we're going to use in order to solve this problem. This graph is an excellent graph because it's going to show us which formulas we're going to use. In interval 1, we're going to use the formula delta H equals M times Cp times delta T. We're using this formula because do you notice that the temperature is going from 40 to 0? There's a change in temperature. Whenever there is a change in temperature, we're going to use MCP delta T. Here's another example. Right here. Isn't the water increasing in temperature? So we're going to use MCP delta T. And lastly, when we increase the temperature of the gas, we're also going to use MCP delta T. Now a problem arises when we're going to look at this interval right here. We have water as a solid becoming liquid water. There's a phase change going on. Do you notice that during a phase change there's no delta T? There's no change in temperature. That means we can't use MCP delta T. Instead, we're going to use the formula mass times heat of fusion. Okay? We run into the same problem right here when liquid water becomes a gas. Again, that occurs at constant temperature, so there's no delta T. So in that case, we're going to use the formula mass times heat of vaporization. Now, we need to know the values of some constants. For example, we need to know the specific heat of ice, which is 2 joules per gram degrees Celsius. We need to know the Cp of water, that's liquid water, that's 4.184 joules per gram degrees Celsius. And we need to know the Cp of steam, which is 2 joules per gram degrees Celsius. So now these CPs are going to take place. We're going to use these right here, right right here, and right here. Now, we need to know heat of fusion and we need to know heat of vaporization. The heat of fusion of water is given as 334 joules per gram of water, and heat of vaporization is equal to 2260 joules per gram. Notice there's no degrees Celsius in this because, remember, no change in temperature, so we don't need to take care of that at all. Remember, a phase change occurs at constant temperature. Let's solve delta H for number 1. Interval 1, right here. Delta H equals M times Cp times delta T. Now, what's the mass of the water? 15 times the specific heat of ice, because remember, right here we're talking about solid ice, so that's equal to 2 joules per gram degree Celsius. And our delta T. What's our delta T? Now, I want to erase this so you can see. Do you see that we're going from 40 to 0? Remember, delta T is final minus initial. Our final temperature is 0 minus our initial temperature, negative 40. So 0 minus a negative 40 is positive 40. So now all we do is multiply it together and we get 1200 joules of heat are needed to change 15 grams of ice at negative 40 degrees to ice at 0 degrees Celsius. There is no change in phase yet. Now let's solve for delta H for this interval right here. This is when the ice is going to be melting. There's no change in temperature. So the formula we're going to use is delta H equals mass times heat of fusion. Now that's a constant that I'll give you, or the California reference tables, they'll be on there. Now remember, the heat of fusion is 334 joules per gram. So this is a really easy problem to solve. We have 15 times 334. So in other words, in order to change ice to water at 0 degrees Celsius, and when we're talking about 15 grams, it's going to take 5,010 joules. Let's now do the third interval. We now want to heat up the water, okay? Notice that the temperature is increasing, and we're going to take it from its melting point 0 up to its boiling point 100. What's the formula? M times Cp times delta T. The mass is 15 grams times the heat capacity, which is 4.184 or 4.2 if we round. What's delta T? Delta T is final minus initial. Well, the final temperature is 100 minus my initial temperature, which is 0, so we're going to get 100 degrees Celsius. So now we're going to multiply them together, and we're going to get a delta H of 6,300 joules of heat are needed to change 15 grams of water at 0 degrees Celsius to 15 grams of water at 100 degrees. Now it's time for interval 4. This is where we're going to change water at 100 degrees to steam at 100 degrees. Again, no change in temperature, no delta T. So we can't use MCP delta T. No, instead we're going to use the formula delta H equals mass times heat of vaporization. Now the heat of vaporization of water is a constant. Again, that'll be given to you, 2260 joules per gram. And we have 15 times 2260. And when we multiply that together, we get 33,900 900 joules of heat are needed just to vaporize the water. Our last calculation is interval 5. This is where we're going to increase the temperature of steam at 100 degrees up to steam at 30 degrees. Delta T, final minus initial, 130 minus 100. So for this interval, the temperature of the steam has changed 30 degrees. Here's our formula. Delta H equals M times Cp times delta T. Our mass is 15. Our specific heat of steam is 2. And our delta T is 30. So when we multiply this together, we get 900 joules of heat are needed to increase the temperature of steam at 100 degrees to steam at 130 degrees. Now this is showing you all the work that I did on a piece of paper when I solved this. Okay, here's interval 1, interval 2, interval 3, interval 4, interval 5, and in order to calculate the amount of heat needed to change 15 grams of ice at -40 to steam up there at 130 degrees, we're going to add them all together. You see right here? We're going to have to add it all up. And I get a total heat needed of 47,310 joules.